Welcome to Advanced Functions. This is going to be Chapter 2, Rates of Change. Now, this is lesson number 1. We are going to talk about determining average rate of change. So also take a look at the slope of a secant line. First of all, what is a rate of change? So in the previous chapter, we did talk about a rate of change to be like slope. Slope, it means you're looking for how steep the line is going to be. The steeper it is, the higher the rate of change, or the higher the slope. So for slope, we define it as m is equal to change in y over change in x, which is dependent variable over independent variable. So under the rate of change, we are going to divide into two sections. First, it's average rate of change, and the second is instantaneous rate of change. So I will be interchanging ARC, average rate change, or average rate of change. Okay. So first, average rate of change. So we looked at it before. The average rate of change in the y variable with respect to the x variable. So you have to always define the domain from one point to another, and the formula is given by ARC, rise over run, which is change in y over change in x. So because this is grade 12, we will be using a function notation. Depending on what the output is, you will be using this formula in terms of given the 2 points x1 and x2. Another way to represent average rate of change, we call it a secant line. A secant line is defined as a line that passes 2 points on either a curve or a line. So for example, let f at x be a function, and you have to define 2 points, point 1 and point q. Now the slope of a secant line that passes through point P and Q is defined as the average rate of change. Again, same formula. Okay, so in the question, when I ask for find the slope of a secant line, it's asking you to find the average rate of change between the two defined points. So let's see. A rock is launched vertically upward. The height h in meters at the time t in seconds. The rock is given by the height formula, the equation. Find the average velocity over the third second of motion. So the third second of motion, it means, so there's 0, 1, 2, 3, and 4, let's say. The third second motion means over here. Okay, so it's in between 2 to 3 seconds. So first, let's write down the average rate of change. So in this case, we're looking for velocity, is defined by h2 t minus h t1, which is t2 minus t1. So we already know what the second time. So the height at 3 seconds minus the height at 2 seconds. 3 minus 2. Height at 3 seconds. So we're plugging in 3 into t minus 10, 3 squared. When you simplify, it will give you 210 meters. The height at 2 seconds, it will be 100 times 2 minus 10 2 to the squared, and that will give me 160 meters. So therefore, it's going to be 210 minus 160 over 1, which in turn, 50, don't forget the unit, it's going to be meter per second. So therefore, the average velocity is going to be, so average velocity over the third second is going to be 50 meter per second. Okay, so you want to be mindful about the wording of the third second of motion, which means it's in between 2 and 3 seconds. And because it's average, you have to find the output at 3 and 2. Okay, so it's basically like a slope formula. Now, when we are also looking at rate of change, we need to distinguish if the function is increasing or decreasing. Now, we can define the function to be increasing if the average rate of change is greater than 0, meaning it's positive when you're reading the graph from left to right. So as I'm reading, what's happening to the graph? The graph is increasing. So therefore, the average rate of change is going to be positive. On the other hand, if it's a decreasing function, we could say that the average rate of change is going to be less than 0, meaning it's going to be negative at the defined domain. Again, as I'm going from left to right, the graph is going down. So therefore, the average rate of change is going to be negative. Okay. So let's do second example. So Joy drains water from a hot tub. The tub holds 1,600 liters of water, and it takes about 2 hours for the water to drain completely. The volume of water remaining at the tub, and so in t time in minutes is shown in the table and the graph. Calculate the average rate of change in volume during the 30 to 90 seconds. So again, let's write down the formula. Average rate of change is equal to fx2 minus fx1 over x2 minus x1. So we know the two defined domain. So average rate of change, so we're working in terms of volume. So we will be putting volume 90 seconds minus the volume at 30 seconds. And then 90 minus 30. So because we're not given an equation, what you can do is you can look at the table or look at the graph. So it will be more accurate to look at the table of values. So at 90, we have 100 liter, minus at 30 minute, we have 900 over 60. Okay, so once you simplify, it's about negative 13.3. And don't forget the units, it's liter, because the numerator is volume, liter, per denominator is time, which is minute. So what does this mean? So you can say, therefore, the average rate of change in volume from 30 to 90 seconds is decreasing at 13.3 liter per minute. So when you are using the word decreasing is representing this negative here. You never say decreasing negative 13.3. It's one or the other. Okay, so because it's a word problem, I expect everyone to use decreasing in replace of the negative. at 13.3 liter per minute.